Greetings and welcome to the Chemistry 222 online lecture for Chapter 10. And in this chapter, we're going to look more detail at both solids and liquids to complement the gas chapter we just got through. And in addition, we're going to look at something that's actually pretty important that you may or may not have heard of before. And that subject is called intermolecular forces. Intermolecular forces are really necessary if you wish to turn like liquid into a gas or gas back into a liquid. Also, it helps to explain why solids are kept together so tightly and gases are not kept together so tightly. So a very interesting chapter. Without further ado, let's get into what this material is all about. When it comes to the three states of matter, solids, liquids, and gases, all right, there's definitely differences. And we've talked about this off and on since the beginning of Chem 221. The kinetic molecular theory basically says that solids are very close to each other. Liquids, there is an attraction between them, but of course it's not as intense as solids. And then gases basically have no interactions between each other at all. And every time you wish to turn a solid into a liquid, it's going to take heat. And in our world, of course, that means that it's an endothermic process. And the same thing if you wish to turn a liquid into a gas, you also have to add heat. You can also reduce the pressure, it's true, but most of the time it's adding heat and stuff. Now, the opposite process, going from gas to liquid, liquid to solid, usually is done through cooling. So those kind of processes and stuff, if you cool it down, that means that energy is being released. And that's kind of interesting. So one thing I want to point out right away here is that every time you go solids to liquids, liquids to gases, it's going to be an endothermic process. You need to add heat. On the opposite, every time you go gas to liquid, liquid to solid, actually you get energy out and it's exothermic, and that's why you have to cool things down a little bit. All of these phases, though, are the same material, and we talked about this a little bit in the last section. If those little purple dots represent water, then the crystalline solid on the far right would be ice, solid water. Of course, liquid would be liquid water. And on the far left, you would have gaseous water or vapor. But they're all H2O. The difference between the phases is nothing more than the interaction between the particles, the molecules that are interacting. So that's what we're going to focus on, like what makes the solids so strong, what makes gases basically have none, and how to interconvert the two of them together. Sometimes you hear the term condensed phases used for solids and liquids. If you remember, even since Chem 221, the density of liquids and solids, usually solids go up to like about 20 grams per centimeter cube, some of them a tiny bit more than that on the periodic table. Liquids usually 1 gram per milliliter is the density of water. Sometimes you can get down to smaller densities for liquids. But both of those density ranges are a lot greater than the density for gases. We saw the densities for gases are usually represented in grams per liter, so a lot less mass per volume, if you will. So condensed phases just means you have the molecules tighter together. That's all it means. The punchline of why these phases are different and what's going on is intermolecular forces, and we'll talk about that here in a little bit. When it comes down to solids versus liquids versus gases, there's two things we have to really think about to understand why some compounds are more likely a solid, say at room temperature, than a gas. And it really comes down to the kinetic energy of the particles, like how much energy is inside each one of them. And it also comes down to the strength of the attraction between the particles. So like we said, solids are a little tighter, they're held on a little closer to each other, and gases basically have no interactions with each other, all right? And that is going to be the intermolecular forces. Temperature is a big time component because temperature will definitely increase the kinetic energy of the particles, and it will tend to break up the strength as you raise the temperature. And of course, lowering the temperature would be the opposite. So the strength of the attraction versus kinetic energy of the particles, which is basically a temperature phenomena, becomes really important. So an intermolecular force is a different kind of a force than we've talked about so far. We've talked about a lot of intramolecular forces, ionic bonds, covalent bonds, even the metallic bonds we talked about, all of those are intramolecular. Intramolecular means inside the molecule, all right? And those bonds, those types of forces are very, very strong. But what we're going to talk about mostly in this chapter are intermolecular forces. And intermolecular forces are the forces between two molecules. So these forces are generally not as strong as the intramolecular forces, but are they important? Because these are the attractions that keep the molecules together. Intermolecular forces are not chemical bonds, all right? Intermolecular forces are just helpful guides to keep molecules together when we wouldn't maybe expect them to be. And again, they're nowhere near as strong as intramolecular, the ionic, covalent, metallic. So this is a new type of force, all right? We haven't talked about these so far, and you're going to see that they're pretty important. So earlier we talked about how there's basically a competition between the kinetic energy of the molecule and the attractive forces between the molecules. And let's call the attractive forces for what they are. They're intermolecular forces. So you can see here we've got a solid, a liquid, and a gas. And the EK there at the top, which stands for kinetic energy. Solids have the lowest kinetic energy. All right, there's not a lot of movement like holding them around. Then liquids have more kinetic energy, more movement, more variability, if you will, and gases have by far the highest kinetic energy. They're just all over the place. Now contrast that with below. It says the intermolecular attraction. These are the forces now between the molecules. Solids have the highest IM forces by far. Liquids are then in the middle, and gases have no or low intermolecular forces. This last part here on the bottom is kind of important, and I want to highlight it. We're going to assume in Chem 222 and Chem 223 that gases have no intermolecular forces working on them. And that's a fairly good assumption. It's not totally perfect, to be honest, but it works really well for this class. If you go past Chem 223 and you talk about intermolecular forces, gases do have those forces working on them, but they're usually a lot less than liquids and solids. But again, we're going to assume gases have no intermolecular forces, solids have the strongest intermolecular forces, and liquids are in between. So going back to the picture we showed earlier, the intermolecular force, and by the way, it's an intermolecular force between two HCl bonds. These intermolecular forces can be used in a lot of different ways. They will help us to understand differences in boiling and melting points. They'll help us to understand the process of vapor pressure, which is useful for when you turn liquids into gases, as an example, and even things like viscosities, the resistance to flow. And in the companion and online, there is a handout called the Intermolecular Forces Guide, the IM Forces Guide. And I do recommend you check it out. The IM Forces Guide has all the names of the different intermolecular forces we're going to run into, and it's done in a flow chart. So you can kind of go through and see from the flow chart which force you have, and we'll talk about more about this here in a little bit. The first of the intermolecular forces we're going to look at is what's called the ion-dipole intermolecular force. And if you look at the name ion-dipole, this is the force between molecules where one molecule is an ion, i.e. it has a positive or a negative charge, and the other molecule has a dipole. And dipole, if you remember from previous sections, dipole is nothing more than something that's polar, all right? And that's the first big clue I want to give everybody. If you see the term dipole in this class, or in this section, I guess, more importantly, dipole means that something is polar. So you've got something with a charge, it's an ion, and something that's polar, it's got a dipole, ion-dipole force. So an example of the ion-dipole force is up there in the upper left-hand corner. That's a sodium ion, an Na+, it's got a charge. You've got water, which is very, very polar, like we talked about before. And we also talked about how water has a slightly negative side and a slightly positive side. And those little delta symbols there on the top, delta minus, delta plus, they represent approximately where those partial charges are. So the partial negative side of water is attracted to the positive ion on the sodium ion, and this is called the ion-dipole force. In Chem 221, we talked about hydrated systems where water will basically surround an ion and pull it away from the ionic lattice. These hydrated ions are the result of the ion-dipole force. And this is no small feat because it's difficult to pull the ions away from the bulk ionic compound. And you can see here's the positive ions. In this little picture, the positive ion in the middle is being attracted to the negative side of water, which is basically the oxygen, pulling that cation away. And over on the right then, here's the anion. Anion is negative. It's being attracted by the positive dipoles on water, which is essentially the hydrogens, also being pulled away from the ionic lattice.
When a gas phase sodium ion enters water, it becomes surrounded by water molecules, or hydrated. The ion-water connection results from ion-dipole forces indicated by a dotted line. It is difficult to determine the number of water molecules around a hydrated ion, but 6 is a good estimate for most cations.
They feel that generally 6 water molecules are needed to surround an ion to pull it away from the ionic lattice, and there's scientists that do a lot of studies with this, believe it or not. But anyway, for our purposes, just realize that ion-dipole results when you have something polar, usually water, but not necessarily. Anything polar would work, basically pulling on, if you will, an ion. And the ion can be a positive cation, like sodium, but it can also be a negative ion, like chloride we saw a little bit ago. Ion-dipole is really important. Again, it pulls the cations and anions away from the lattice, and usually there's about 6 molecules per cation or anion, and that's fine. In a personal note, I really like the colors of metal ions. That's one of the reasons why I think I became an inorganic chemist, a person that studies metals. And you can see there's the picture with iron, cobalt, nickel, and copper. The colors of these solutions are really fantastic. And those are all due to water molecules surrounding the metal and pulling it away from whatever anion it was. So, all right, ion-dipole force, my favorite ion force. No, I'm just joking. I don't know if it is or not, but it is what results in the cool colors that are the hallmark of transition metals. And we'll talk more about those in Chem 223 as well. So, to sum this all up, ion-dipole is the first of our ion forces. And if you hear ion-dipole, that's the interaction between something with an ionic charge, something positive or negative, and something with a dipole, something that's polar, like water is a common example, but it could also be like acetone, ethanol, anything that's polar.
Hydrogen chloride molecules are polar. When HCl molecules in the gas phase are cooled, the kinetic energy of the molecules can no longer overcome the dipole-dipole forces between them. The opposite ends of the molecules attract each other and coalesce to form a liquid.
Dipole-dipole forces is the second of our intermolecular forces. And dipole-dipole means you've got something polar interact with something else that's polar. And this is an example of HCl. So Cl is much more electronegative than hydrogen. So chloride is the negative side and hydrogen is the positive side. And when 2 HCl's come together, the negative part of the chloride, there we go, and the positive part of a second HCl make a bond, all right? And this little ... dash line in the middle, that's the intermolecular force. That is the dipole-dipole intermolecular force. And this force is really helpful because normally HCl is a gas, but it can be turned into a liquid. It will only turn into a liquid if those intermolecular forces start kicking drawing in and keeping the HCl molecules together. So instead of wandering around randomly, you can then form the intermolecular forces which turn the gas into a liquid. A lot of times you have to, of course, cool it down, all right? You have to lower the kinetic energy of the molecules to make the intermolecular forces kick in. Dipole-dipole forces are pretty strong, all right? I would argue they're not as strong as ion-dipole, but they are very important, and all dipole-dipole interactions involve two polar species. So so there are quite a few examples of polar species. It's a good thing to remember. Here's an interesting effect of the dipole-dipole force. And there's essentially a series, two compounds here in brown, and there's also two compounds below in green, all right? And compare the brown ones to the green ones here, all right? So what I mean by that is N2 and CO. When it comes to boiling, all right, there's basically two factors that affect boiling points. One of them is going to be this molar mass, like how many grams per mole, because boiling is kind of like taking a molecule and throwing it into the air. And if the molecule is light, that will be an easy process, but obviously if it's a big molecule, that's going to be harder to do. And in N2 and CO, you can see the molar masses are identical, all right? So the boiling points, negative 196 versus negative 192, there should be no interaction with the mass here, all right? It's not the mass which is doing it. And the difference between those boiling points is attributed to the fact that CO is polar. Oxygen pulls differently than carbon. In nitrogen, the nitrogen pulls the same as the other nitrogen. Nitrogen N2 is nonpolar, so you don't have the dipole-dipole force. But when CO comes in contact with other COs, you do have the dipole-dipole force. So if you're going to turn liquid or solid CO into a gas, you have to overcome the intermolecular forces. And you can see it takes 4 degrees of temperature more to make CO boil than it does N2. And again, if this was just molar mass base, you would think that those boiling points would be the same. But because CO is polar, it has the dipole-dipole force, makes it a little bit harder to boil. You see that also in the next two examples. Bromine and iodine monochloride are both about the same molar mass, all right? 160 versus 162. But look at the difference in the boiling points. It's almost 40 degrees, like about 60 to about 100, all right? That's a big, big difference. And that 2 gram per mole difference in molar mass is certainly not going to be enough to do it. ICl, once again, is polar. So ICl is going to have dipole-dipole forces working on it, and bromine does not. Bromine and nitrogen are both nonpolar. So ICl is also experiencing dipole-dipole interactions. That's why that boiling point is so much greater than the almost identical molar mass bromine. Here's a question you might see from this chapter. The strongest intermolecular force in acetone is, and there's all these different names right here, and we're going to go through what these names are so far. So what you need to do in this structure, on this problem, is you should ideally find out if the molecule is polar or nonpolar. And one way to do this is just to draw good old Lewis structures. We're still in Lewis structure world. If you do that, you'll see that acetone has a double bond O in the middle. There's a methyl group on both sides. That's what the CH3 there is, and that's what the CH3 right there is. And then there's a carbon-oxygen double bond. And again, my drawings are so bad here, I apologize, but this is a ketone, if you remember from the organic chemistry chapter. Anytime you have a carbonyl, all right, and that can be ketones, aldehydes, carboxylic acids, etc., etc. But anyway, carbonyls always make the molecule polar. All right, so C double bond O is enough to make the whole thing polar. And things that are polar are going to have an intermolecular force best described as dipole-dipole. The ion-dipole force, the first one, would be for something like a potassium ion, K+, and water, something with an ion charge and something polar. And the other three down there we're going to look at here in a little bit. So if in doubt, draw the Lewis structure out, see if you can find if the molecule is polar or nonpolar. Acetone is certainly polar. We would expect it to exhibit dipole-dipole force. Dipole-dipole is pretty strong, but you can get an even stronger version of dipole-dipole if you have a hydrogen connected to the right kind of atom. So there in the little picture, there's an X and an H, and a Y and an H. So if X and Y are the right kind of atoms, you get like a supercharged version of dipole-dipole, which is even stronger. If the X and Y are nitrogens, oxygens, or fluorines, you end up with what's called hydrogen bonding. And hydrogen bonding, again, is like a supercharged dipole-dipole. It's many orders, I would argue, of magnitude larger than a regular dipole-dipole force. So hydrogen bonding is going to definitely affect boiling points, melting points, and stuff like that. And we'll see some examples of it. On the right-hand side are some examples of hydrogen bonding. The top one is pretty important. That's two water molecules interacting with each other. So notice that here's the hydrogen. It's connected to an oxygen, i.e. it's NO or F. The oxygen is also one of the NOs and Fs. So this is prime hydrogen bonding material. Water exhibits very strong, we're going to see hydrogen bonding. The next one down is ammonia. So hydrogen is connected to nitrogen, one of the magic three, and another ammonia comes in, pretty strong. But you don't have to have water to water or ammonia to ammonia. Here's an example of ammonia and water, and that's another hydrogen bonded species, and the bottom one is too. So there's lots of different interactions that are possible. Because fluorine can only handle one bond, the only example of fluorine involved with hydrogen bonding will be an HF, hydrogen monofluoride, or hydrofluoric acid, depending on what it's in. But HF is definitely a possibility. Most of the hydrogen bonding things are for oxygens with hydrogens, i.e. alcohols and groups like that. You can also have nitrogens with hydrogens, and those are amines, if you remember in the organic chemistry chapter. Here's a question you might see. Which of the following should exhibit hydrogen bonding in the liquid state? The liquid state is important because only liquids and solids for Chem 220, Chem 223 will have intermolecular forces. The gas form of any of these would not have hydrogen bonding. They wouldn't have any of the intermolecular forces at all. So if you go through this list, well, here's good old HF, which is the only fluorine version. Fluorine connected to a hydrogen, that's absolutely going to have intermolecular forces. Remember, you have to have hydrogen connected to nitrogen, oxygen, or fluorine. So that's the only time. Now, the second one, C2H4, there are hydrogens, but the hydrogens are connected to carbons. That compound is ethene, if you remember from organic chemistry, but hydrogen isn't connected to NO or F. So B is not going to be one of the possibilities. Now, C is where the structure, the Lewis structure, is very important. You do have oxygen, which is one of the three big ones, NO or F, and you have hydrogens. But C is an ether. It's a methyl group, CH3, connected to an oxygen and then connected to another methyl group. You have a carbon-oxygen-carbon linkage when you draw out the molecule. And again, you have to have oxygen connected to hydrogen to make hydrogen bonds possible. So drawing out the structure of C, you're going to find that's not it. Again, you're going to have a carbon, oxygen, carbon in this molecule, and you have to have oxygen connected to the hydrogen directly to have hydrogen bonds. The last one, methanol, you definitely do have the OH. That's what you need for a hydrogen bond. Again, you need to have fluorine connected to hydrogen as an A. You have to have oxygen connected to hydrogen or nitrogen connected to hydrogen. So A and D are both good answers. There's going to be more than one that has hydrogen bonding. And again, the liquid state or solid state is important because those are the ones that are going to have these intermolecular intermolecular forces. And hydrogen bonding is one of the intermolecular forces. It's a special version of dipole-dipole, and it only works again for N, O, and F.
Ice is held together as a solid by hydrogen bonds. When ice melts to liquid water, the regular, relatively open structure of ice collapses. Liquid water can be more efficiently packed and denser than ice.
Water has all kinds of interesting phenomena due to hydrogen bonding. And one of the most interesting things is shown in the graph right there. The lower part there is solid water, ice, and the upper kind of curved part right there, that's liquid water. And they feel that the strong intermolecular forces in the solid ice, all right, and remember solids are usually stronger intermolecular forces than liquids, it actually keeps the water molecules at bay, keeps them at very rigid areas. So you melt the ice, all right, and then the water forms, and you don't have as strong as intermolecular forces, so the liquid molecules actually get closer to each other. And that creates this really bizarre break in the density. You can see that ice is not the smaller density, and then water on the top is the bigger density. A result of this is that if you put an ice cube in water, it floats. And that may not seem like a big deal to you. You're like, oh yeah, whatever, Russell, that's really interesting. But this is actually one of the few substances that has a solid able to float on liquid, all right, i.e. the solid density is actually smaller than the liquid density. So the smaller density things go to the top and the bigger density things goes on the bottom. Most elements and compounds, the solid density is greater. So the solid compounds would sink in the liquid version of the same substance. Water is definitely unique. Not unique, there's a couple examples, but man, it's very, very rare to have this kind of phenomena. So next time you plop an ice cube in your liquid water, think, whoa, because that's really what you should do. It's really wild how it happens.
A plot of the boiling points of the group 6A hydrogen compounds shows a trend. Based on this trend, we would expect the boiling point of water to be here. In reality, H2O's boiling point is much higher. This is a consequence of water's stronger hydrogen bonds.
This graph also kind of gives me the chills. It's kind of cool. So let me explain to you here why I'm kind of freaking out a little bit. But anyway, this shows group 6A, which are called the chalcogens. It shows different combinations of each of the first four chalcogens with hydrogen. So H2Te would be tellurium in the middle, H2Se, H2S, and then H2O, of course, we'll talk about in a little bit. All of these compounds, the central atom, the group 6A nonmetal, it has two lone pairs. So they're all tetrahedral bent, all right? They're all polar. But like we talked about earlier, if you're going to boil something, it comes down to two factors. It comes down to the molar mass, like how heavy they are, because it's kind of like throwing it in the air, all right? And it comes down to the intermolecular forces. So if you look at just H2Te, H2Se, and H2S, you definitely see like a curved trend, all right? And that's because Te is a lot heavier than, say, H2S, the sulfur, and so H2Te is going to take more energy to push in the air to make it boil than H2S. So you would expect in this video then that water would be like down here, maybe minus 100. And again, this is a boiling point, all right? But as we all know, since we live with water all the time, water is anything but minus 100. It's more like up here at positive 100. That's where it boils. And this is not what you would expect based on the trends of other group 6A nonmetals. And the difference here for water that makes it so special, even higher boiling point than H2Te, which is a lot heavier, by the way, are the hydrogen bonds, all right? The hydrogen bonds keep the water together a lot more, and it's much, much more difficult to make the water boil than it is H2S, H2Se, and H2Te. The other three, H2S, H2Se, and H2Te, they all have regular dipole-dipole force, and that's a strong force in and of itself, absolutely. But because water has this supercharged hydrogen bond version of dipole-dipole, that makes it its boiling point just crazy high, crazier high than even the H2TE, which is quite a few grams per mole larger. So hydrogen bonds and stuff, in addition to having the weird ice floating on liquid water phenomena, also creates boiling points, which are much higher, which is kind of cool. Here are other examples of the effect of hydrogen bonding. So the top one up here, here's water, all right? And like we saw in the last version, water is a lot higher boiling point than H2TE, even though the molar mass of water is much, much, much less than H2TE. But remember, it's not just oxygen that does hydrogen bond. It's also fluorine and nitrogen. So here are the corresponding hydrogen halides. So HI is pretty high, and HBr a little less because it's not the same molar mass, HCl, but then bam, HF quite a bit higher. And again, that's the result of hydrogen bonds. HF holds on to other HF molecules a lot better than HCl, HBr, or HI. The other one right here, this is ammonia, another hydrogen bond, and you can compare it to the antimony trihydride, arsenic trihydride, phosphorus trihydride, ammonia, again, a lot higher. However, when it comes to group 4, all right, which does not exhibit hydrogen bonding, then you do see kind of this downward trend. Tin, germanium, silicon, and carbon are all group 4A, and carbon, unlike nitrogen, fluorine, and oxygen above it, does not have hydrogen bonding. So these have just normal kind of downward slope. You can see that more or less it's kind of like a line, which is what you would expect normally. So hydrogen bonding, pretty important when it comes to molecules.
DNA is composed of 2 sugar phosphate chains that are oriented in opposite directions. This orientation permits complementary base pairs to be connected by hydrogen bonds. Hydrogen bonds are responsible for the helical shape of the molecule.
Hydrogen bonds actually keep our DNA together, and that's no small feat. These hydrogen bonds are strong, so it keeps the sides of the helix together, but they're also not so strong as to keep like differences and DNA changes and stuff to happen, which is cool. In 2013, they actually started some pictures, if you will, of actual hydrogen bonds. The lighter white ones are actual intramolecular bonds, but the intermolecular hydrogen bonds are these kind of wispy little white things that hold them together. And that's kind of cool. So this is a home movie picture, if you will, of hydrogen bonds, and chemists get all excited by it. Woohoo. But anyway, they are important. They keep a lot of things together. And in biochemistry, you'll definitely see a lot more examples of the importance of hydrogen bonds. There's more than just ion-dipole, dipole-dipole, and hydrogen bonds. It's also possible to have a non-polar substance basically forced into being a little bit polar. And if you take something that's pretty polar, i.e. it has a pretty strong dipole, and you place it next to something non-polar, you can induce a dipole in something which normally doesn't have a dipole. So the next type of force we're going to look at here is when you've got something polar and it basically forces something non-polar to take a little bit of polarity. This is an important example for the fish. Here's water, which is very, very polar, and it's getting really close here to oxygen. And oxygen has just 2 oxygens, so it's non-polar. But if the water molecule gets close enough, it can induce a dipole. So all of a sudden now, oxygen is trying to shift its electrons away from the negative dipole of water. So oxygen ends up there with a positive dipole, that little delta plus, and there's more negative electron density, the delta minus, on the far side. This is actually another kind of force, and it's important for the fish because oxygen normally wouldn't get down to the fish in the water, all right? Oxygen non-polar and water polar, they don't usually get along. However, enough oxygen is polarized a little bit, if you will, by water that it can actually then get the fish down to the water and the little fish can breathe.
On average, the electron cloud of an O2 molecule is distributed symmetrically across the molecule. The molecule is not polar. A water molecule, which is polar, repels the electron cloud, causing it to be asymmetrically distributed and thereby induces a dipole in the O2. This shift allows O2 to be weakly attracted to the water molecule.
This kind of force is referred to as a dipole-induced dipole force. And let's break that down. Dipole, like we talked about earlier, means polar. Induced dipole means that it doesn't have a dipole by itself, i.e. it's nonpolar. But you can induce, you can create a dipole in this nonpolar substance if you put something polar next to it. So dipole-induced dipole means something polar and something nonpolar together. And I want you to think nonpolar when you hear induced dipole, because you're having to make a dipole where one didn't exist before. No small feat. Oxygen in water is a great example. Also nitrogen in water. Anytime you have something nonpolar and something polar together, that's the dipole-induced dipole force. This is another example. This is taking iodine and dissolving it in ethanol, an alcohol, all right? And this is used sometimes in medical facilities. Now, iodine is nonpolar to iodine atoms. There's no polarity, no differences. Ethanol is very polar. Ethanol has an OH, which is actually one of the hydrogen bonding categories. So ethanol is actually pretty polar as well. You can induce a dipole in the nonpolar I2, and I tried to draw a little funny circle there to show it. The electrons are trying to get away from, in this case, the oxygen on the alcohol. So it basically creates a slight positive charge next to the alcohol, and the electrons trying to get away from them, from the negative charge, then creates a slight negative dipole on the other side. Remember how electrons trying to get away from other electrons? A lot of chemistry is about those kind of interactions. And in this case, that creates the dipole-induced dipole force. But it does allow the iodine to dissolve in ethanol, which can be used for purifying things, stuff like that.
An iodine molecule has, on average, an electron cloud that is symmetrically spread over each iodine atom. I2 is not polar. The attractions or repulsions between the atoms of I2 molecules can distort their electron clouds. Dipoles can thereby be induced momentarily in neighboring molecules.
Two nonpolar species together, if you lower the temperature enough, can actually induce dipoles on each other. It's like they begin to get so close that they begin to actually then talk to each other, if you will, and it creates another kind of intermolecular force. And this kind of intermolecular force is called induced dipole. And if you wish to abbreviate that as IDID, I totally understand and recommend it, actually. Anyway, induced dipole is the weakest of all the forces, because making two things which are nonpolar be slightly polar, i.e. inducing a dipole on them, is pretty tough. And it's not usually something that happens real readily. So these are considered one of the weaker forces. But if you're going to take something nonpolar and turn it from a gas into a liquid, you have to start thinking about intermolecular forces, something to make those gas molecules tighter into a liquid form, and they feel it's the induced dipole force. Now, because this is such a weak force, there are several different names for it. One of the names is called London dispersion forces, and that's fine, or also dispersion forces is fine. I'm going to use induced dipole for my representation of it, but do realize it has different names. But the important part and the final part is that induced dipole is just what happens when two nonpolar substances come together. And again, this is where polarity now becomes more and more important as we go on in chemistry.
In the flask is solid iodine. In the test tube is ice. When we heat the iodine, its weak induced dipole forces are overcome, and the iodine sublimes into the gas phase. The gas recondenses as a crystalline solid on the cold test tube.
Solid iodine has an induced dipole force. Again, the only phase that doesn't have an intermolecular force are gases. So solids and liquids will always have some kind of intermolecular force. And because iodine is nonpolar, we would call that an ID, induced dipole force. If you heat the iodine gently, it turns into a gas. And it doesn't take too much because, again, the forces are really weak. But in the middle there, they have what I've always referred to as a cold finger, all right, which is basically a test tube with ice. So the gaseous iodine condenses back to a solid in the middle, and this is a good way to purify your iodine if you need to. So you're basically turning the weak forces into a gas temporarily. The ice then condenses the gas back to a solid. This is the sublimation process. Some substances go straight from gas to solid and solid to gas. We'll talk about that more in a little bit. Pretty cool. The magnitude of the induced dipole does tend to help to figure out if something's going to be more likely to make a solid or not. And again, higher molar mass will usually have higher induced dipoles, and that's kind of interesting. So if you look down there, on the left-hand side, there's a series of halogens, F2, Cl2, Br2, I2, and those are all nonpolar. And notice how the boiling points increase. So as molar mass goes up, the boiling point goes up too. And all of those are intermolecular forces, are ID. On the next one over, you're seeing the noble gases, all right? And the noble gases, as they get bigger, it gets harder to make them boil, takes more energy. So little tiny helium with almost very, very small grams per mole, about 4 grams per mole, 4.6 Kelvin is where it turns from a liquid into a gas. So very, very easy to turn that one into a gas. But bigger gases then take more energy. So xenon has a higher boiling point. Krypton would be next, etc., etc. Of these 4 examples, which one would you expect to have the highest boiling point? All right. And really what it comes down to most of the time is that either the type of the intermolecular force, that's number 1, and number 2 is the molar mass, higher molar mass, higher, lower molar mass, smaller. Well, all of those are noble gases. So they're all induced dipole. They're very, very nonpolar. So this question is not about the intermolecular force. This one's about then the other part, the molar mass. And if you look on the periodic table, xenon is the biggest molar mass, about 131 grams per mole. So we would expect it to have the highest boiling point. It's going to take the most energy to get that larger grams per mole into the gas phase. This is a summary of the intermolecular forces we've seen so far, and there are other ones out there. We'll talk about those in a little bit. However, ion-dipole, one of the stronger ones, and that's what's responsible for making like sodium chloride dissolve in water. All ionic compounds dissolving in water are the result of the ion-dipole force. Remember, ion means something with a charge, something positive or negative. Dipole means something polar. Hydrogen bonding is a special form of dipole force, and hydrogen bonding only occurs when you have nitrogen, oxygen, and fluorine connected to hydrogen. So if you have that, then you have hydrogen bonding. All polar substances, when they interact with other polar substances, at the very least have dipole forces. But if your polar substance has an N, O, or F connected to hydrogen, then it gets the extra special hydrogen bonding and you get a little bit more bang for your buck. Dipole-induced dipole means something polar. Dipole is next to something nonpolar, something induced dipole. Oxygen in water, nitrogen in acetone. Anytime you have something nonpolar and something polar together, dipole-induced dipole. And then finally, the last one, which one other name for it is dispersion, which is induced dipole, or the London force. Those are for just nonpolar species. So Cl2, Br2, we looked at the noble gases. One more we haven't looked at is that if you have pure ions, so like pure sodium chloride, that's an ion-ion force. And also if you have a pure metal, like pure iron or pure chromium, that's called a metallic force. Those two forces we're going to consider to be the strongest force of all right? That would be even stronger than ion-dipole. Those are mostly for solids, and here we're looking mostly at liquids and gases and stuff, but those are the same kind of things. Just realize that on the top, even above ion dipole, is going to be the ion/metallic force. We'll consider those two equivalent, even though that's not the best analogy, and we will talk about both of those forces more in the future. So this is the kind of question that you might see. When potassium chloride dissolves in water, what kind of intermolecular forces are observed, or what kind of intermolecular bonds are formed? All right, and this is a good question. So what you have to think about is what kind of forces exist in KCl and what kind of forces involve water, okay? Well, KCl is an ionic compound. You can have positive Ks and negative Cl chlorides, all right? So KCl is ionic. And water, as we've seen, is not only polar, but it has those special hydrogen bonds. So water polar is like a dipole. So KCl ion, water dipole, you probably figured it out. This is going to have the ion-dipole forces when they come together. Now KCl separately would be the ion-ion force, which is something we haven't talked about yet, but we will, I promise. Water separately would have hydrogen bonding, but when they come together, the ion-dipole force is what's going to rule this problem. So let's now change gears a little bit and talk more about liquids. And liquids are really interesting. So in a liquid, which is different than a gas, arguably a little bit, there's some special constraints. In a liquid, the molecules constantly moving around. You have pretty good intermolecular forces. Now remember, gases move around a lot, but they didn't have any intermolecular forces, or at least in Chem 222 and Chem 223. Also compared to gases, liquids, the molecules are pretty close together. It's almost impossible to compress a liquid. Now you can compress gases. You can take 3 liters of gas and compress it down to a milliliter or something like that without too much difficulty. But liquids are pretty hard to do that. Also, liquids don't fill the container. Like you pour the liquid in and it takes up whatever volume it needs. A gas will completely fill the container if you quote unquote pour it into a container. Quite a little bit different there between liquids and gases.
According to the kinetic molecular theory, the molecules of a solid are locked in place, though they have motion. Molecules of a liquid are closely associated with each other, but move relative to one another. Molecules of a gas move independently and occupy a much larger volume than those of a corresponding liquid or solid.
So you can probably see then that to turn a gas into a liquid, you would probably have to lower the kinetic energy, which would be one possibility, or you'd have to somehow make intermolecular forces kick in to hold the molecules together. And we'll talk about the transformations and stuff between the two in a little bit. If you're going to turn a liquid into a gas, you have to break the intermolecular forces in the liquids. Remember, liquids have intermolecular forces and solids as well, but not gases. And if you break intermolecular forces, that's going to require some energy. So going from a liquid to a gas is going to be endothermic. It's going to take energy to make that happen. And the practical, more common term for turning a liquid into a gas is evaporation. So evaporation just means you're turning a liquid into a gas. It's endothermic, and that's kind of interesting. On the other hand, if you want to take your gas and turn it back into a liquid, you're going to have to form intermolecular bonds to make those gas molecules kind of stick together. You're going to have to remove some of the kinetic energy inherent to the gas molecules. You can do that through cooling or something like that. But in the process, you're going to end up releasing energy. The energy of those gas molecules is going to be released as the intermolecular forces form. So actually going in a condensation, energy is actually released. So evaporation means liquid to gas, and it's endothermic. Condensation means taking the gas, turning back into a liquid, and believe it or not, that's exothermic. Energy is released. If you're going to turn a liquid into a gas, all right, you have to have enough energy to break the intermolecular forces which hold them together, all right? And that's maybe not a strong feat. Another thing about turning a liquid into a gas is that if it's hard to turn a liquid at the bottom of the liquid into a gas. Usually what happens is it's the outside, i.e. the perimeter, if you will, between the liquid and the gas. So this little picture right here, the liquid is below below the line and the gases are above. And the liquids that will be able to turn into a gas, you'd have to give them energy, and they'll be on the outside, the surface of the liquid, and they'll go up. But some of the gas molecules on the top will say, oh, I really want to go back to the liquid phase, so they go back to the gas phase. So you can see in that little picture, some of the arrows go up, that's liquid going to gas. Some of the arrows go down, that's gas going to liquid. This is a very dynamic process, all right? And again, going from the liquid to the gas, you have to break those intermolecular forces. It's going to be endothermic.
Molecules of a liquid have a range of kinetic energies. Some have enough energy to overcome intermolecular forces. If these high-energy molecules are at the surface of the liquid, they can escape into the gas phase. This is an endothermic process.
This is an open container, so the gas molecules are escaping, going off into wherever they go, all right, and that's fine. A closed container, we're going to see later, is a different story. But again, in the chemical theory of the KMT, only the surface molecules are actually able to break free. The molecules down below, if they got enough energy, they would just smack into another liquid molecule. The energy would be transferred through something like momentum from physics, and it would still remain a liquid. But the process of going from liquid to a gas, endothermic, takes energy to break the intermolecular forces. Like we saw with gases, liquids have a range of energies, and they're temperature dependent and all that kind of stuff. So in the graph on the left, we have a blue line and a red line, and the blue line represents the distribution of energies in a liquid at a lower temperature, and the red line represents the distribution of energies at a higher temperature. And also, I want to have you focus on the dotted line right there, and that represents the energy required to turn a liquid into a gas. So you'll see that at the higher temperature, you have a lot more percentage, if you will, of molecules past the dotted line. And those are the ones that, in theory, can turn from a liquid to a gas. They have enough energy. Most of the lower temperature ones don't have enough energy to turn into a gas, so they stay as a liquid. But notice down here, there's a really small area, I'm going to kind of highlight it messy there, of molecules that do have enough energy to turn into a gas. And we're going to talk about those here in a little bit. The important thing here is that kinetic energy, the energy of the molecules, is proportional to temperature. So you keep raising the temperature and you're going to have more molecules able to break from the liquid to a gas. But even at the higher temperatures, all right, you're always going to have some of the higher temperatures going to want to stay there. I mean, eventually they're all going to go, all right? But at first, there's always going to be some small percentage that really wants to stay a liquid. Only when you keep adding energy, do they all turn one way or the other. So this is, again, how scientists think about it. And we're trying to think about like the amount of liquid molecules that turn into the vapor or gas state. So this brings up the idea of what's called vapor pressure. And vapor pressure is the pressure exerted by the little bit of gas above a liquid. And like we saw in the last picture, even at the lower temperatures, there's always going to be a little bit of gas. So some of the molecules have enough energy to break into the gas. As you increase the temperature, you have more and more molecules able to have a gas. Remember, pressure is the direct result of gas. So this is the gas above a liquid. And all liquids, arguably anyway, have a little bit of gas above them. Now, you always have an equilibrium vapor pressure possible if you put a flask lid, if you will, on the container. So in this example here with the liquid, there's a stopper. It's keeping the gas molecules from going away. And if you let it wait just a little bit, the amount of evaporation equals the amount of the condensation, or the speed or rate of evaporation equals the speed of condensation. Your vapor pressure will be a constant. It's a measurable amount. You can measure it in atmospheres or millimeters of mercury, and the vapor pressure is actually really important to understanding how liquids and gases interact.
In a closed container, molecules move back and forth between the liquid and gas phases. If the rates of crossover are equivalent, the overall amount of substance in each phase remains constant. The system is said to be in a state of dynamic equilibrium.
This dynamic equilibrium just means liquids are constantly turning into gases and gases are constantly turning into liquids. And again, as long as you have a closed system, i.e. a stopper on your flask, then you will have this. And this vapor pressure does some really interesting things when it comes to chemistry.
The liquid in the butane lighter is in dynamic equilibrium with the gaseous butane, which has a vapor pressure of about 2.4 atmospheres. When the valve is opened, butane gas escapes from the lighter, the system goes out of equilibrium, and liquid butane rapidly evaporates into the gas phase. When the valve is closed, the system quickly comes to equilibrium again, with the pressure of the butane vapor equal to 2.4 atmospheres.
A cigarette lighter is actually a pretty interesting kind of device because you have in there butane. Butane is just barely a liquid at room temperature. But above the butane, you have vapor pressure. Some of the butane has enough energy to turn into a gas. So when you're ready to use the cigarette lighter, you push the thing down and a spark happens. The butane comes off. A combustion reaction occurs, which is butane plus oxygen, making CO2 and water. But anyway, the flame appears, all right? And the flame appears because the gas, the vapor pressure over the liquid is trying to escape. It's burning up as it goes through, no problem. Well, after a while, you're done with your lighter, so you close it off again. The equilibrium vapor pressure is reestablished, so the next time you light up, all right, the cigarette lighter comes back. Another thing is that when your cigarette lighter is just about done, at first, like nothing happens, so you put it down, but then later on, maybe you forget that it was supposedly dead, and you light up, and oh, there's a little bit there. Sometimes the vapor pressure reestablishes itself enough to make a last-minute light. It's kind of interesting.
As heat is added to a beaker of water, the vapor pressure of the water increases, thereby increasing the rate of evaporation. If enough heat is added, the vapor pressure of the water equals the atmospheric pressure. At this point, large bubbles of vapor begin to form in the liquid, and the liquid boils.
Vapor pressure, like all pressures, go up with temperature. So we saw in the gas section, PV equals nRT. Pressure and temperature are proportional. So temperature goes up, your pressure goes up. And this applies to vapor pressure as well. If the vapor pressure equals the atmospheric pressure, which for 1 atmosphere is 760 millimeters of mercury, this, when vapor pressure and atmospheric pressure are the same, this is when a liquid boils. So you start seeing liquids boil when the atmospheric pressure and the vapor pressure of the liquid are the same. And this is kind of an interesting process. So maybe you've heard that at some cities you have to boil things longer, all right, if they're higher elevation, like Denver, Colorado, for example. Well, this is why. The pressure, the atmospheric pressure at Denver is less than 1 atmosphere. So it boils quicker. You're trying to get heat to the food or whatever, so it takes a little extra energy. So boiling, we can actually talk about what boiling is. Boiling is where the vapor pressure of the liquid equals the atmospheric pressure. And that's kind of interesting, as you're going to see here in a little bit.
In the flask is water heated to about 55 degrees Celsius, well below water's normal boiling point. We use a device to evacuate the air from the flask. The water boils, though its temperature remains at around 55 degrees.
Water boils at 100 degrees Celsius normally, all right? But let's say you wanted to make water boil at, in this case, 55 degrees Celsius. You can do that by lowering the external pressure, because remember that boiling is when the vapor pressure equals the atmospheric pressure. So if you lower the atmospheric pressure, it takes less vapor pressure to reach it, and it's going to boil faster. So water can boil 55 degrees Celsius, 65, whatever you want, if you play with the atmospheric pressure. So this is an interesting thing. The normal boiling point for a compound is when it boils at 1 atmosphere of pressure. But you can have boiling points at all different values if you change the external pressure. In my world of chemistry, if I wanted to get rid of the extra solvent, sometimes I could lower the pressure, the solvent would boil off without hurting my compound. It was a really nice kind of purification technique, but there's lots of other uses for it too, as you can see.
Heating the liquid water converts it to a gas, which pushes molecules of air out of the container. The inverted can traps the gaseous H2O when we place the can in cold water. The temperature change converts the gaseous water into liquid water, which occupies a much smaller volume. The can is crushed by the pressure of the atmosphere.
This is kind of a cool chemistry demonstration you can do at your house if this is anything you're interested in. But anyway, what they did is they took an empty aluminum can and they put a little bit of water in it, all right? And then they heated the water. In this case, it was over a Bunsen burner. And so what happened is the liquid water in the can became a gas. And the gas occupied the entire volume of the can, all right? Well, then what they did is they took the can with the gaseous boiling water, fumes inside it, and they inverted it and put it in cold water. So what that did is it shocked the system. The gas molecules turned quickly into a liquid, and liquids don't have the pressure associated with it. So liquids go down to almost nothing. The external pressure just crushed the can like that, and you get some pretty interesting kind of results, as you can see. So yeah, so if you turn a liquid into a gas, the gas takes up all of the volume. But then if you can somehow turn the gas back into a liquid, the volume goes way, way down. There's no more pressure pushing back, and the outside pressures, which are around us all the time on the Earth, crush the can. This has huge implications. These are actually big train cars, all right, that were quote unquote empty with just a little bit of some kind of substance in them. And what happened is maybe on a hot day or whatever, someone thought, oh, I'll clean these cars and make them look pretty. Well, as you clean them with probably cold water, the cold water made the gas inside condense down, just like we saw in the can a little bit ago, and squish, everything was crushed. So I can imagine there were a lot of bad words said those days. Just be aware. You should be very careful if you have to clean the cars and stuff. Make sure you don't do them on the wrong kind of day. Don't crush your train cars. This is a graph that shows the vapor pressure for three different substances at different temperatures. And you can see that on the left is diethyl ether, the middle one is ethanol, an alcohol, and the right one there is water. Now, at the top, in this little line right here, the dotted line, those are the normal boiling points of those compounds. So the normal boiling point is where the substance boils if you're about at 1 atmosphere of pressure. But you can also see the different vapor pressure curves. And notice their curves, all right? They're going slowly up there. The vapor pressures are increasing with temperature. And also you can see the difference here in the intermolecular forces. So let's think here about the intermolecular forces. Diethyl ether has an oxygen connected to carbons. Oxygens usually have 2 lone pairs on them. So diethyl ether is polar. It doesn't have hydrogen bonding though, because the oxygen isn't connected to a hydrogen. So we would classify diethyl ether as dipole-dipole. Both ethanol and water have OHs, and that's one of the magic hydrogen bonding combinations. But water is extra special here because water has 2 OH bonds. So you can imagine that water has like 2 sources of hydrogen bonding possible, while ethanol has just 1. So here, water is actually the smallest grams per mole of all these compounds, but it has the higher boiling point because in theory it has twice the hydrogen bonding of ethanol. Pretty interesting. These curves, the red curve, green curve, and blue curve, they are vapor pressure curves, and they show all conditions of pressure and temperature where the liquid and vapor are in equilibrium, all right? So the vapor pressure is rising with temperature, all right, because pressure and temperature are proportional, and remember, vapor pressure is a pressure of a gas. When the vapor pressure equals the external pressure, that's when you can have boiling. And at 1 atmosphere of pressure, you can see like diethyl ether boils at 34.6. But if you wanted diethyl ether to boil at 0 degrees Celsius, in theory you could do that. You would have a vapor pressure just under 200 millimeters of mercury, and you should be able to make it boil. So you can change the boiling points of all these things by changing the external pressure. When the external pressure is 1 atmosphere, which is 760 millimeters of mercury, the temperature that it boils then is called the normal boiling point. And most of the time when you hear people talk about boiling points, they're normal boiling points, i.e. what is it at 1 atmosphere of pressure. And you can see that the boiling points are increasing based on their intermolecular forces, like we talked about. The intermolecular forces go from dipole-dipole, which is the diethyl ether, to a hydrogen bond on the ethanol, to multiple hydrogen bonds in water. So the intermolecular forces are certainly playing a factor when it comes to the boiling points, just like we've seen with all the other things so far. These intermolecular forces hold on to the other molecules stronger, so it takes a little bit extra energy to make them boil. So on the basis of the relative strengths of the intermolecular forces, the predicted order of decreasing boiling points for the following substances is, and there's 3 substances here we're looking at. The first one is methanol, which is another type of alcohol but with a methyl group on it. We also have methane, CH4, and we have hydrogen, H2. All right. Now we want the order of decreasing boiling points. So we want the highest boiling point first and the smallest boiling point last. Well, you can probably see that methanol, CH3OH, has a hydrogen bond, and that's going to be stronger than the other two, which don't have hydrogen bonds. So I'm going to predict that since we want strongest to weakest, all right, or highest boiling points to weakest boiling points, methanol should be the first one because it's got the strongest intermolecular forces. It's going to be more like ethanol in that graph up there. CH4 and H2 are both non-polar. CH4, if you draw out the Lewis structure, is a carbon in a tetrahedral form with hydrogens all around. So it's symmetric, it's non-polar. And H2 is literally 2 hydrogens together. That's also non-polar. So both CH4 and H2 exhibit induced dipole forces. So if they're the same force, then we look at the molar mass, like which one is heavier, which one is lighter. Because remember, boiling is kind of like pushing something into the air, and lighter things are easier to push into the air than heavier things. So I would look at the molar masses of CH4 and H2. So CH4, carbon is 12 grams per mole in the periodic table. Hydrogen's about 1, and there's 4 of them. So that would be 16 grams per mole for methanol. Hydrogen, 1 gram per mole hydrogen is about 2. So methane, CH4, is heavier. So I would predict that methanol, again, is the heaviest. The next one would be methane. And finally, hydrogen would be the last one. So answer A here would be what I would go for. And again, we used intermolecular forces to first pull methanol away from CH4 and hydrogen. After that, since CH4 and hydrogen were the same induced dipole force, we would then look at the molar mass to see which one was heavier.